Whether it's pharmaceuticals or cosmetics, production methods are similar across the chemicals industry. Despite complicated technology, the actual chemical reaction commonly takes place in a so-called batch reactor or boiler. That means even in large-scale facilities, chemistry works basically like it does in the lab. The reagents flow together in a vessel, but that doesn't provide optimal mixing. The vessel contains a variety of substances in different concentrations, called concentration hotspots, as well as a range of temperatures, called thermal hotspots. Experts describe this situation as reduced process control. In order to ensure the most efficient use of raw materials and energy as possible in the chemicals industry, process control must be continuously optimized. Chemists at the company Airfeld Microtechnik in Wendelsheim, Germany, have developed their own system of carefully controlling the reaction of combined chemicals. The Modular Microreaction System, or MMRS, consists of several components through which reagents flow inside tiny channels. The small, stainless steel parts carry out a variety of functions, like that of a mixer, heat exchanger, and sensor. The chemists place a special reactor in the middle of this unit. The channels are only a few millimeters wide in all of the components. That allows for a very rapid exchange of substances. And because of the large surface-to-volume ratio, the chemicals are quickly able to absorb and give off heat. The chemists place the entire unit under an exhaust hood. Chemicals flow through hoses into the tiny channels. The flow plate microreactor used in the unit is also equipped for what's known as lithiation. This reaction is often used for the production of active ingredients in pharmaceuticals. The substrate, bromoanisole, flows through the reactor in channels that are only a few millimeters wide. At the same time, the reagent, butyllithium, flows into the reactor. Right after the two chemicals are combined, they flow through a meandering structure just a few tenths of a millimeter wide. That leads to a rapid mixing of the two reagents. During the reaction, lithium replaces bromine. That creates an intermediate product. The reaction also releases great amounts of heat. And that leads to the destruction of some emerging molecules. If the process is not cooled, more raw materials are needed to retain desired amounts of the product. And that makes efficient cooling vital for the reaction's success. In the flow plate reactor, the chemical reaction takes place in a small channel on a large flow plate that is cooled from below by a cooling agent. The large surface area ensures an optimal heat exchange, and the chemicals can be cooled with less energy than needed in a large vessel. That not only saves energy, fewer raw materials are also needed since the process creates fewer unwanted byproducts. Shortly afterwards, acetone flows into the channel. It also mixes with the intermediate product in a meandering structure. The acetone is taken up by the intermediate product. The desired carbon compound is created, and that results in the end product, an organic compound with very specific characteristics. If this experiment had taken place as usual in a batch reactor, a conventional vessel, a low temperature of minus 80 degrees Celsius would have been necessary to adequately cool down the reagents. Because of the Lonza reactor's efficient cooling, a low temperature of only about minus 20 degrees Celsius is enough to stabilize the lithiation process. Lithiation is a good example of very fast organometallic reactions, where a large amount of dislocation is necessary to extract energy from the batch. But that's not energy efficient. The microreactor allows you to release heat very quickly and work under strictly defined conditions, and that lets you manufacture products with greater energy efficiency and fewer byproducts. The chemists use other reactors too for their experiments. This Miprova reactor contains 8 long channels, 1.5 millimeters high and 12 millimeters wide. The engineers insert 3 rubber-like grids. That creates a highly complex structure in the channel's interiors. The reactor is again mounted inside the modular microreaction system and placed under the hood. This experiment is focused on ethoxylation, a reaction that is commonly used in the production of materials for the cosmetics and paint industries. Manufacturers use toxic and highly flammable ethylene oxide for this purpose. The ethylene oxide flows through the channels together with another reagent, a type of alcohol. The complex grid structure ensures a thorough cross-mixing of the reagents. And that leads to an even distribution of reagents in the channel system. As a result, there's no formation of concentration hotspots, and the reaction is controlled. The ethylene oxide is taken up by the oxygen atom of the alcohol group. This procedure repeats itself several times. A polymer is formed. Since the reagents are homogeneously distributed in the reactor, the same amount of molecules always accumulate on an alcohol group. Identical polymers are formed with the desired length and with few byproducts. Because of its structure, the Miprova offers a very large surface-to-volume ratio of 2,000 square meters of reactor wall surface per cubic meter of fluid volume. That means the extreme exothermic reaction can be adequately cooled. That's vital, since the starting product is highly explosive. The reactor enables an easily controllable and safe process flow with few byproducts. Since reactions in the flow plate and Miprova reactors take place in small channels with a diameter of just a few millimeters or micromillimeters, the process is highly defined, and that makes upscaling relatively simple. The channel cross-sections in the reactors are simply enlarged, or several channels are arranged parallel to each other. These so-called micro and milli-reaction technologies make possible the production of several thousand tons of a given end product each year, from pharmaceuticals and fine chemicals to petrochemicals and food chemistry. Micro and milli-reactors have great potential as process-intensifying instruments in the chemicals industry. Estimates claim that about 50% of fine chemicals and pharmaceuticals could be produced faster, cheaper, and more effectively through a continuous process in micro and milli-reactors. Each year, the German chemicals industry generates revenues of some 190 billion euros. There are several providers of micro and milliprocess technology in Germany. Their technology can contribute to substantial savings of energy and raw materials in the chemicals industry and help secure Germany's position as the world's third largest chemical supplier.